Welcome to today's lecture. So today we're going to be talking about boosting models, specifically AdaBoost. As we'll see, these are super interesting and very powerful ensemble models. Let me just give you a quick roadmap of where we're heading. So we're going to talk about boosting algorithms in general and what they do and what they are. Then we're going to focus on the heuristics behind the AdaBoost or adaptive boosting. We're going to look at the actual algorithm, and then we're going to discuss the theory behind it, because I think, as a mathematician, but also I feel like it's super important in order to truly understand AdaBoost to actually look at its proof and some of its interpretation. So kind of dig deep into the theory. And then finally, we're briefly going to discuss how you can implement adaptive boosting in Python. So what are boosting models? So boosting models are another example of these ensemble models. Basically, they aggregate multiple lower level learners into a stronger and more sophisticated model. Okay. One of the big differences between boosting models and random forests or bagging is that in the bagging and random forest models, you're fitting a bunch of weaker models essentially independently of one another. So you can fit them parallel to one another and then just aggregate their result at the end of the day. On the other hand, boosting models are what we call sequential in nature. What that means is that you fit one model or train one model after the other. And the idea is that each predictor or weaker model that you fit tries to learn and somehow improve upon the predecessors. Okay? And there are many types of boosting models. Some of the more popular ones are adaptive boosting, gradient boosting, XGBoost, and there's a bunch of others really. So for today we're gonna focus exclusively on adaptive boosting. And so there are many tutorials out there on adaptive boosting, but I feel like so there are some really good tutorials as well, but I think what I'm gonna try to do here, I'm gonna try to hit this trifecta. I'm gonna talk about the heuristic behind adaptive boosting, and then I'm going to dig into the theory behind adaptive boosting to understand how it works and why it works, and then finally I'm going to talk about Python implementation. I think many tutorials out there kind of do a subset of this. So what is the heuristic? So let us focus on this picture here. So there's many ways that a learner or a predictor can learn from its predecessors. So in adaptive boosting, the way a predictor tries to learn from its predecessors is by focusing more and more on the training samples that were misclassified by its predecessors. So as you move deeper and deeper into the model, sort of these future learners are focusing more and more on these hard cases, right? So specifically, so you start here with the training data, okay? This is your original training data set that you have. You fit a model. It could be a decision tree, logistic regression, and random forest, even it can be another ensemble model as well. And then you make predictions on this training data set, okay? So what happens here is now you update two things. You update the weights which are associated with the training samples, and you update the weights or these coefficients that are associated with the actual learner or the model that you fit on the stage before it. And once you update those, the next model is going to focus sort of, or is going to pay a little bit more attention on the data sets here, or on the training samples here that were misclassified by the first model, okay? And that's reflected on the weights that were updated. So we'll see that later on when we dig deeper into the model, how that actually comes about. And then you repeat this process, as long as you want. I mean, as many you can fit as many models as you want. For example, you can fit 100 decision trees. Okay. So, right. And as we'll see, basically, as I said here, and this is kind of the main heuristic or philosophy behind adaptive boosting. Each next predictor tries to focus on the portions of the data set where its predecessors did worse. All right, great. So let's talk about the algorithm itself first. So suppose that we have a training data, and I want to apologize if there are any typos here. I'll try to catch them and address them if I catch them, I guess, as I'm going through this. But if you see any, please point them out. So suppose that we have n training points, where each data point has n features, and the target is basically takes two values. So we're talking about a binary classification problem. Okay, so it can be 1 or -1. So suppose that we have capital M classifiers, where again the output of each classifier is either 1 or -1. So first off, there is something that you want to kind of minimize, right? So there's this what we're going to call the 0-1 loss function. So it's 0 if your learner or predictor is predicting what it's supposed to, it's predicting correctly, and it's 1 if it's not, if it's misclassifying basically the point xi. In other words, the 0-1 loss function just counts the instances that were misclassified. And ideally, you would want this to be 0. So in an ideal world, once you would want a predictor basically that yields a 0-1 loss function. Okay, so here is the actual algorithm, and there are slight variations of this of AdaBoost out there. So we're going to stick with this one. Initially, you want to initialize the weights somehow. So these are the weights that are going to be associated with our training samples. So basically we have as many weights as we have training samples, and these weights are sort of going to reflect which training samples are being classified correctly. Oh, sorry about that. And which training samples are being misclassified, and we'll see that a little bit later how that comes about. There's different ways to initialize these weights. So you could initialize them to be 1, all of them, or to be 1 over n, where you kind of normalize them. Step 2. So for each of the weak learners, what you want to do is you want to pick, take your weak learner and fit the weak learner in such a way that you minimize this objective function. Okay. So let's pay attention to what's happening to the numerator. So this guy here is the indicator function. This just basically keeps track of all the cases that we're misclassifying. So if our classifier does really well, then EM, this is the error rate, is really small because this guy is mostly 0, and we have the weights here which are associated with those training points. Okay. If the classifier is doing really poorly, then you have a high error rate. So once you have fit the model and you've computed the error rate, then you compute this, what I call worthiness coefficient. This is the weight that's associated with the actual model, okay? Not with the training samples, but with the actual model. And it's supposed to signify just, or to reflect just how well did the model do. So in other words, if the model did really well, that means the error rate is really small, so this fraction here is really large, so log of that is also large. So basically alpha m will be larger if EM is smaller. Similarly, alpha m will be small, actually negative, if EM is large. Okay? That's just telling you that that model didn't do well. This eta here is what we call a learning rate, and I think it was not there in the original when this model was originally introduced, But actually you can also do other variations of this model. For example, ideally actually in practice what you want to do often is you want to kind of schedule this learning rate. You don't want it to be fixed through all iterations. You want it to decrease maybe in some way. So, but anyways. So once you've basically fit the model, computed the error rate, and computed these weights associated with the model, with a learner, then you want to update these weights which are associated with the training samples. And it seems a little bit convoluted maybe, but let's just go through it. It's not actually complicated at all. So let's consider two cases. So suppose that the training sample or training instance xi was classified correctly. Then if it's classified correctly, this guy here, this indicator function is just going to be 0. So this exponential is going to be just 1. So the weight on the next stage is just going to stay the same as the weight on the actual stage. In other words, the weights of training instances that are classified correctly don't change. Now, suppose that this particular instance was misclassified. Then there are really like three sort of scenarios we need to consider, and there's a little bit maybe of intricacy there. So suppose that the model did well, okay? If the model did well, so first off, I mean, when we're dealing with the cases that were misclassified, this guy here is always 1. So you can't forget about it, just think of it as 1. Now what happens to this yi fmxi? So think about it a little bit. If if xi is misclassified, that means that this product, yi fmxi, is always going to be negative, okay? And that's why there's a little bit of there's kind of an intermediate step that we need to do in one of the situations. So let's consider the first scenario. So suppose the classifier fm did really well. If the classifier did really well, then this alpha m is going to be positive. So here alpha m is going to be positive, yi times fmxi is going to be negative. So this whole thing is going to be positive, and it's going to be bigger than 1, okay, because the exponent is positive. So the weights are going to increase. So in other words, the weights of the training samples that are misclassified are increasing, at least in the instance where the model is doing well. Now let's suppose let's suppose we're in the other situation where the model does really poorly. Say, for example, f of m misclassifies 70% of the training data. Then before you go here to update the weights, actually what you do is you flip the sign of your model. Why do you want to do that? Well, think about it. So if your model is misclassifying 70% of your data, for example, if it's instead of being 1, it's saying is -1, instead of being -1, it's saying is 1. Then by flipping the sign, actually you automatically have at your hand a model that classifies correctly 70% of the time. So with that in mind, then this guy is going to be again negative. I mean positive now, but alpha m is going to be, once you flip the sign, then you're again in the same situation as before. So this whole guy is again positive, and e to a positive guy, to a positive number is again larger than 1, so you're increasing the weight. The only scenario where you kind of want to avoid, or I guess you wish you could avoid, is if the model is doing exactly like 50-50, because you're really not learning anything in that situation. So bottom line, the takeaway here is that the data that are misclassified, when you update the weights get larger, okay, to reflect the fact that those particular instances were misclassified. Okay, so how do you make predictions? Well, say you have a new data point, x, then you just go and check what each of these individual predictors gives you, and then you sum those up based on the weight, okay? So if you get a positive guy here, then you predict for that particular instance to be positive, 1 in this case. If this is negative, then you predict for that to be negative. Now, if you wanted to pick yi to be either 0 or 1, you could define it this way as well, your final predictor. Okay, so one of the things, when I first learned about this model, one of the things that I had difficulty understanding just looking at this model, without digging deeper, was this idea that the model pays more attention to the misclassified data on the next step, basically, meaning like what we mentioned here. This idea that at stage 2, the weak learner basically at stage 2 tries to pay more attention to the training samples that were misclassified in stage 1. I couldn't really, I think maybe I'm just not smart enough, but I like looking at here, I mean it's here, it's definitely here, but it was not super clear to me like how exactly was that happening in the algorithm. I mean, sort of, like when these learners are being fed, I mean, I couldn't sort of visualize that, how that was happening. So I had to dig deeper into these explanations and the theory behind this AdaBoost, and that's what I want to do here, because I think that's kind of maybe the only way, at least for me, to really see that. And if you can see it by just looking at this algorithm, then you're definitely like smarter than I am, so that's good. Okay. So there are a few ways, I think, to interpret AdaBoost, and one very good one is via a loss function. So suppose, so I guess, okay, yeah, as I said, like one way, I guess, to think of the AdaBoost is as a procedure to optimize some loss function, and specifically to optimize this exponential loss function. Okay, so suppose that you have this training data just as before. So in this case, now when we are fitting the model, we need to optimize the following objective function. So basically this is now the objective function, and we need to optimize this objective function with respect to two things. These weights associated with the models, with the weak learners themselves, and the weights associated, these W's basically, associated with the actual training data. Okay. So here basically, maybe this is just kind of like a, I don't want to say like a discretized version of this exponential, right? So y is this yi, and then f of x here is just this. That's what appears here. Awesome. So AdaBoost is what we call a sequential greedy algorithm. What does that mean? So it does not try to find sort of a global optimum for this guy. What do I mean by that? So it does not try, I guess, to find a global set of alpha m's and these wi's that optimize this objective function, but rather it at each stage, okay, so at stage m+1, for example, it tries to find the parameter alpha m+1 and these weights wi's that result in the smallest objective function at that stage. Okay, so it does not try to look any further. So it is possible, for example, that you can find different parameters alpha m and omega i's that could result in a lower overall, objective function if you would sort of look deeper and further as well. But that's more costly. And so this is important because once you pick, like for example at stage m, once you pick these alpha m's and omega I m's, then those are fixed. Those do not change anymore, okay? So first off, so then the goal, I guess, as I said here, is to optimize this LXM, but LXY, but let's first talk about why is this enough, okay? Because, recall that our actual goal is to like at the end of the day, we want to minimize the 0, 1 loss function, but it's actually just easy to see, it's rather obvious that this exponential loss function is bounded by the 0, 1 loss function. So minimizing Lxy, you're really in turn minimizing this 0, 1 loss function as well. Okay, so we're finally at kind of my favorite part of this, where it becomes a little bit like clearer, this idea that each weak learner improves upon its predecessors by focusing on the subset where its predecessor did worse. So suppose that m plus 1 is the classifier that we need to add at step m plus 1, okay, that we need to fit to our data. Then the objective function that needs to be optimized is this e. All I've done here is I've separated the portion at stage m, okay? And the reason I've done that is because, recall from what we just said before, this coefficient here is now static. That does not change, so it's a constant. And we're just going to call it omega I or wi m plus 1. Okay? And if you just rewrite this, again, if you separate the mth term here, then this omega I m plus 1 is proportional to omega I m e minus y alpha m f m x I. And recall here, this is very similar. It should look familiar. It's almost identical to this, except for this guy here. Okay. Great. So keep this in mind. Omega I m plus 1 is proportional to the weights of the training samples on the previous stage times this extra coefficient. Okay. So now here some algebra. So I'm not gonna go step by step, I guess. But this objective function here, first thing I do here is I rewrite this as a sum of training samples that get classified correctly and training samples that get misclassified. And again, some simple algebra here. You can rewrite this as this sum and this coefficient here. Okay, this is kind of the highlight, really. Why is this the highlight? Because here it actually becomes more or less clear why fm plus 1, okay, will try to optimize, or it will pay attention more, or will try to do better at the training samples where the previous classifier did worse. Okay, so let me just, that needs to be fm plus 1. Give me just 1 second because it's kind of bugging me. All right, why is that the case? Well, observe that to optimize E, okay, this guy is constant, like we just said, it's constant, it won't change. So to optimize E, or to optimize E with respect to this classifier fm plus 1, is equivalent to optimizing this term. Awesome. Let's just look at this a little bit. What did we say here? This omega I m plus 1 is proportional to these omega I m's at the previous step. Now suppose that at this instance xi, okay, the previous algorithm fm did poorly. It was misclassified, okay? So this omega I m for that particular instance will be large, right? Okay. Because it will be large, it is in the best interest of the algorithm to try to make this guy 0, since it's trying to optimize this guy to make this as small as possible, okay? So in other words, it's gonna work harder to classify correctly those points that were misclassified before, because these basically have higher coefficients here. So I think at least this is kind of my take on it. You know, if you have a better explanation, you can definitely let me know. Okay, And then the rest basically is just calculus. So to find the actual value alpha m that minimizes e, you just you find the critical points of this equation, and then it turns out to be exactly what you want it to be. Awesome. So the rest of the lecture is basically just Python implementation. And I'm going to run through it fairly quickly because we've done things like this before. So, and it also takes a little while to run these guys. I've already completed everything, so I'm just going to briefly go through it. So here I'm just importing the standard library, so here as well. And I'm going to use this airline satisfaction data set that we've been using in the last few lectures, and also for comparison purposes as well. So the next few lines of code are just taking this data set and pre-processing it. So at the end of the day, once you scale it, this is what you end up with. You have 23 columns. And I'm going to also separate a validation set that I'll just use to kind of gain an idea of how well the model is doing on a set that it has not seen during the tuning stages. So the goal here is going to be, I'm going to fit AdaBoost classifier with base learners, with a few base learners, different base learners, like a decision tree, logistic regression, and random forest. So one thing that I didn't mention is that it is actually possible to overfit AdaBoost as well. While I think, maybe not. Yeah, anyways, if you pick too many estimators, you can still overfit it. So you gotta keep that in mind when you're building these models. So that's why you always want to use like cross-validation and tune the parameters basically. So the downside is that it takes actually a while. Since you're fitting, a bunch of estimators on the background, it takes a while for even to run this one once. So you need some computational power, but other than that, it's what it is. Okay, so here we're fitting AdaBoost classifier. So if you just do Shift Tab here, these are some of the parameters that go inside there. So it's a base estimator is basically what kind of a weak classifier are you fitting. So here I've picked a decision tree with a max depth of 14. And then N estimators is like how many estimators you want to fit there. So here I'm fitting 200 of those, and then the learning rate basically. And so these two parameters are the ones that you typically want to tune. Okay, but here I'm not going to do it because I'm just kind of illustrating it. But yeah, these are the things that you want to tune via cross-validation basically. So once you run this, this is what you end up with. Okay, so it's not doing too bad, I guess, So here now I'm fitting the same guy, and on the validation set is doing 94. So it's reaching an accuracy similar to the random forest itself. And again, remember, random forest also uses decision trees as weak learners, but in a different way from the AdaBoost. And I'm not sure, how much better you can get with AdaBoost classifier using decision trees as a base estimator. I haven't tried to tune it, but you should definitely give it a try. And it will take a while though. Like if you want to tune these parameters, it might take, especially if you increase the number of estimators here, it may take a few minutes to run this. But I think for random forest from last lecture, if I remember correctly, we were doing around 94. So there's that. And so another base learner that I used here is a logistic regression. And again, when you're fitting these guys, you want to tune all the parameters of your base learner as well as the parameters of that go along with the AdaBoost classifier. And that could take a while if you're doing a grid search here and going over the different penalties, different C's, and different number of estimators, different learning rates. It could literally take like half an hour to do this, depending on how many, what your search space basically. So in this case, again, using AdaBoost as a base learner, we're achieving basically a 0.867 accuracy score. And if I remember correctly, last time when we fit individually just a logistic regression, we're getting something similar. So in other words, in this case, at least with these parameters, we are not improving much, if at all. Maybe we're reducing the variance a little bit, but maybe not even that, using AdaBoost as opposed to logistic regression. Okay, and finally, so you can actually use, another ensemble model as a base estimator. I'm not sure, how recommended that is in general, but it's definitely something you want to try. So in this case, again, I didn't tune this to squeeze all the juice out of this model, but here is where I'm using a random forest classifier with 50 estimator, max depth of 12 and max features of 7, and I'm using 80. Basically, I'm fitting these random forests 80 times, okay? And with a learning rate of 0.25. So in this case, if I do cross-validation with 5 splits, this is what we get. And looking at this graph, actually, it looks like it's doing better than what we got last time from just using random random forest classifier. And so here what I do is I just basically refit this model again into our training data, and I compute the accuracy score on the validation set. And actually, at least at face value, it seems like we're getting almost 1.5% better than what we got last time, or at least 1% higher accuracy than what we got last time. And actually, when I fit this guy here, I ran it a couple of times using different parameters, slightly different parameters, and the different, since we're shuffling here things differently, and it's pretty stable. So it stays around 95. It's always above 95.6. And sometimes it even goes all the way to 96, which tells me that, it's kind of where it's at, really. So it's pretty stable. And, while this is not a significant improvement to fitting a random forest alone, I think while it may not seem like it's a significant improvement, oftentimes what you'll find is when you're trying to fit these, when you're building these machine learning models, is that it's sort of easy to get up to a point, like initially, for example, to achieve, 94% accuracy here on this data set. What you'll often find out is that it's hard, or it takes a lot of work and a lot of data engineering to actually improve that, even to push it by 1%, okay? So here, for example, if we really wanted to always stay above 96%, we'd have to do quite a bit more work and more tuning, and actually even go back to the data set and do some feature engineering there as well. Well, this is it for this lecture, and thanks for listening. I hope you enjoyed it, and I hope you learned something.